This semester, we've learned many techniques for handling different types of integrals, but the fact of the matter is that we still can't find an antiderivative of most functions. And the ones that we can, it's pretty hard. So our techniques for approximating areas by using right rectangles, left rectangles, or midpoint rectangles are going to be pretty important. There are other shapes that we can use besides rectangles that will get us even better approximations. And that's what we're going to study in this section. Quick note about tonight's homework. There are 2 problems that are only in the 5th edition of the text. So if you're using the 6th edition, those 2 problems are typed out at the end of this lesson. So we're going to let left end and right end denote the Riemann sums using n left and right rectangles respectively. We want to approximate the integral from 1 to 3 of 3x squared dx by using left 4 and right 4. We'll shade in some rectangles in these diagrams. So let's first just remember what this means. The integral from 1 to 3 of 3x squared is the area under the curve from 1 to 3. So we're trying to estimate this exact area. So I'm going to start by doing it with left rectangles. So I want to do 4 rectangles. So I'm estimating the area under the curve from 1 to 3 of 3x squared dx is approximately equal to left 4. So I'm going to use 4 rectangles to approximate the area under this curve. So I take my interval from 1 to 3 and I break it into 4 pieces. So 1 to 3, there I broke it into 2, and then I break it in half, each one in half again, 4 intervals. So now I have 4 intervals. Each one has a length of 1/2. And I'm going to build a rectangle over each of those intervals. And because I'm using left rectangles now, I'm going to use the left endpoint of each interval to determine the height of the rectangle. So for this first interval from 1 to 1.5, I'm going to build a rectangle over that interval. The height of the rectangle is going to be the height of the function at the left endpoint, which is 1 in this case. So there's my first rectangle. Okay. My next interval from 1.5 to 2, I'm going to build a rectangle over that interval, and the height of the rectangle is going to be the height of the function 3x squared at 1.5, the left endpoint of the interval. So I go up to the function at the left endpoint, build a rectangle at that height. Okay, next interval from 2 to 2.5, build a rectangle over that interval. The height is going to be the height of f of x equals 3x squared at 2, the left endpoint of the interval. So there's my third rectangle. And my fourth and last rectangle, over the interval from 2.5 to 3, I go up and find the height of the function f of x equals 3x squared at the left endpoint, 2.5 in this case, and that's the height of my rectangle. Okay, so what I'm going to do is I'm going to add up the areas of these 4 rectangles, and that's going to be an estimate of my integral. So each rectangle has a base of 1/2. Okay, so each rectangle is base times height. So it's going to be 1/2. And then the height of this function is the value of 3x squared when x is 1. So it's going to be 3 times 1 squared. Plus my next rectangle, it has a base of 1/2. And its height is the value of 3x squared at 1.5. So 3 times 1.5 squared. Third rectangle, base is 1/2. The height is the value of 3x squared when x is 2. So 3 times 2 squared plus 1/2 times my third rectangle, base of 1/2. The height is the value of 3x squared and x is 2.5. So 3 times 2.5 squared. And this should come out to 20.25. Okay, so now I'm going to do a similar procedure on the same graph. I'm estimating the integral from 1 to 3 of 3x squared dx again, but this time I'm going to use right rectangles, 4 right rectangles. So I've got the integral from 1 to 3 of 3x squared dx. This is approximately equal to right 4. Okay, and I'm going to calculate that by building right rectangles over my intervals. So I'm going to highlight the interval. I want the area under the curve from 1 to 3. Break it into 4 pieces. So I've got 2, 1.5, and 2.5. And over each of these intervals, I'm going to build a rectangle that has the height f of x equals 3x squared at the right endpoint of the interval. So from 1 to 1.5, I'm going to build a rectangle over this interval, and its height is going to be the height of 3x squared at 1.5. Okay, and then for my next interval, 1.5 to 2, build a rectangle whose height is the height of the function at 2. And then we keep doing this as we work our way across here. And 3. So my first rectangle, it's got a base of 1.5, and its height is this value on the function f of x equals 3x squared, this y value. So I plug 1.5 into 3x squared. 3 times 1.5 squared. Next rectangle, base of 0.5, its height is 3 times 2 squared. Just plugging 2 into the function. Next rectangle has a base of 0.5, and its height is 3 times 2.5 squared. And then finally, 1/2 times the height of this last rectangle is the function value when x is 3, so 3 times 3 squared. And we get 32.25. Now I'm going to do a similar method, except instead of using rectangles, I'm going to use trapezoids. I'm going to stick with 4, a little typo in the packet there. Sticking with 4 trapezoids, and I'm going to draw them on the picture, just like I did with the rectangles, and then I'm going to calculate the area of all 4 trapezoids. So I still have my interval from 1 to 3. Break it into 4 equal pieces. And I'm going to build a trapezoid over each interval. So my trapezoid, it's going to have a left height of the function value and a right height of the function value. So I go up to the function on each endpoint, and then I'm going to connect those two with a straight line to build a trapezoid. So I have 4 trapezoids to calculate the area of. And then I have written down the area formula for a trapezoid over here. The area is 1/2 h, where h is going to be the width of my intervals, times base 1 plus base 2. And my base 1 and my base 2 are going to be function values. Okay, so trap 4. My first trapezoid, I'm just plugging into my formula. I have 1/2 times the height, which is 1/2, times base 1 plus base 2. So my base 1 is this height, my base 2 is this height, and those are function values. That is 3 times 1 squared plus 3 times 1.5 squared. My next trapezoid, using the formula, I have a 1/2, and then my h is 1/2, and then base 1 plus base 2, this is base 1, this is base 2. Those are function values, values I get by plugging an x value into 3x squared. So that is 3 times 1.5 squared plus 3 times 2 squared. My third trapezoid, plugging into the formula, 1/2 times h, which is 1/2, times base 1 plus base 2. This is base 1. This is base 2. Those are function values of 3x squared when I plug in 2 and 2.5. So 3 times 2 squared plus 3 times 2.5 squared. And one more trapezoid, plugging into the formula, 1/2 times h, which is a half, times base 1 plus base 2. This is base 1, this is base 2. Those are values of the function f of x equals 3x squared when I plug in 2.5 and 3. So 3 times 2.5 squared plus 3 times 3 squared. So that's a lot of calculations, but a calculator can handle that pretty easily. And that comes out to 26.25.